Hi, we're now in Unit 6 and this is our first video. We're going to build on our knowledge of electronic structure that we learned in Unit 5, and we are going to be looking at chemical periodicity. So what exactly is that? Well, we're going to be looking at properties of elements and patterns that these properties follow on the periodic table. We're going to be looking at 4 properties in this particular video. We're going to be defining and looking at atomic radii, or the size. We're going to look at ionization energy, electron affinity, and electronegativity. So first of all, let's remember that these outermost electrons that we call valence electrons have a great influence on these properties of elements. So if we're going to add one extra electron to an s orbital or to a p orbital, it can have a dramatic effect on physical and chemical properties. Adding an electron to a d or an f orbital doesn't have quite this big of an effect on properties. And so tomorrow in class we're going to do an activity and we're going to be graphing properties of the elements, but we're only going to be looking at elements in the S block and the P block because they're the ones that have the biggest differences. All right, so what exactly is atomic radius? Well, it's the size of an atom, but the way that it is truly defined is it's the radius of an atom, or r, and it's calculated by taking half of the distance between nuclei. Well, it looks something like this. So if we look down here, this is a chlorine-chlorine bond, and so here's a chlorine atom, and the red center is the nucleus of that chlorine atom, and here's the nucleus of another chlorine atom. And so they take the distance between the two nuclei, and if you divide that in half, you would have the radius of the chlorine atom. And so the chlorine atom has a radius of about 99 picometers, so it's very small. And here we have a carbon atom, and measured the same way, its radius is 77 picometers, and so forth. So the sizes of atoms are sometimes reported in a unit that we've not used before, and it's called angstroms, and it's designated by a capital A, which you see here, and it has like a circle over it. That is the abbreviation for an angstrom. And an angstrom is defined as 10 to the negative 10th meters. So if you ever run across that unit, I don't want you to think, what in the world is that? But for instance, the radius of lithium is 1.52 angstroms. But as we saw in the last slide, units can also be picometers or nanometers. All right, so what affects the radius in the atom? Well, I want you to remember a big theme that we're seeing in chemistry, and that's that opposites attract. And we have opposites in the atom. Our nucleus is positively charged from the protons that are located in the nucleus. Our electrons outside of the nucleus have a negative charge, and they are attracted to that positive nucleus. So that electron cloud model that we're using for our atom has our electrons making up the majority of the volume of the atom. But that positive nucleus does have an effect on the size because it is pulling in those negative electrons because the nucleus has that positive charge. All right, now this brings up something called the effective nuclear charge, or Z effective. Now, that positive charge that's felt by these outermost valence electrons is what the effective nuclear charge is. It's not the full positive charge of the nucleus because some of that positive charge from the nucleus is shielded, and so those outermost electrons don't feel the full effect of that positive nucleus because there are some inner shell electrons that are shielding or screening the outermost electrons from that positive nucleus. So here is just a picture of the screening or the shielding effect. So here's our positive nucleus. This green haze here, this is our inner shell electrons, and then the blue is our outer shell electrons. And what's happening is these inner electrons kind of protect or shield the valence electrons from that positive nucleus. Now these valence electrons will feel some of the positive charge, but not the full positive charge of the nucleus, and it's just called the effective nuclear charge. So let's look at some examples of the shielding. Here is the electron configuration for lithium, 1s2, 2s1. This is our valence electron. It's in the outermost shell, and so it's going to be shielded from the nucleus by that 1s orbital. But have a look at sodium. Look at its electron configuration, and its valence electron is way out here, the 3s1 electron. And so all of this here, these inner shell electrons, are shielding this 3s electron from the nucleus. Now granted, sodium's nucleus has more positive charge in it than lithium has, but these inner electrons are shielding the outermost electron from that positive core in the atom. So we would say that sodium's valence electron is more shielded from the nucleus than the valence electron in lithium. So we're going to be looking at trends and plotting trends of atomic radii in class tomorrow. So what affects the atomic nuclei? Well, it's going to depend on how far away the electrons are located from the nucleus, and it's going to depend on that positive charge in the nucleus. So we'll want to keep that in mind tomorrow when we look at the atomic size of atoms as we go across the periodic table and down the periodic table. This brings us to our next property called ionization energy. It can be abbreviated capital IE with a subscript 1. That 1 just indicates it's the first ionization energy. Well, the definition is the energy required to turn an atom into a cation by removing the outermost electron. It always takes energy to remove electrons. It's always an endothermic process. So, ionization energy, the amount of energy required to remove an electron from an atom. So let's go ahead down here and let's see. Calcium has a first ionization energy of 599 kilojoules. So we have to put in 599 kilojoules of energy in order for us to pop off an electron and form the calcium ion with a +1 charge. So again, what's happening is you're taking your atom, you're adding energy in order to knock off an electron, and what's left behind is a cation because you've lost an electron. And for calcium to remove that first electron, it takes 599 kilojoules of energy. All right, but then there's something called the second ionization energy, IE2, and so for calcium, we've already lost one electron, so that's why it has the positive charge. And now the second ionization energy is 1,145 kilojoules in order to pop off that second electron to give calcium its +2 charge. Now, ionization energies, the second ionization energy is always higher than the first ionization energy. We're trying to take away an electron from something that now has a positive charge. So the second ionization energy is always greater than the first ionization energy. All right, well, let's think about ionization energy in terms of metals and nonmetals. Elements that have low ionization energies means it doesn't take much energy to pop an electron off. They like to lose electrons and form cations. So losing electrons would make it maybe more stable. Maybe losing an electron would make the atom isoelectronic with, say, a noble gas. So this should be reminding you of what we learned in our last unit, that metals form cations and they form them easily. So metals have lower ionization energies. Now, nonmetals, they really don't like to lose electrons. They prefer to gain electrons. So ionization energy to take an electron away from a nonmetal is typically high. So we're going to be looking at trends in ionization energies tomorrow. And the size of that ionization energy is going to depend on very similar things that we saw with the radius. We're going to have to think about effective nuclear charge and shielding and where these electrons are in position relative to the nucleus. Are they in a high energy level far from the nucleus or a low energy level close to the nucleus? These are things to think about for tomorrow's activity. Our next property is called electron affinity. So affinity just means that you really like something. So like I have an affinity for chocolate. I like chocolate. Well, electron affinity is the energy change when an electron is added to an atom. In some cases, atoms really have an affinity for an electron and they really want electrons. So energy is released when you add an electron because that makes the atom more stable. In some cases, atoms don't want electrons at all, and it would take a lot of energy for them to add an electron to something because they really don't want an electron. Well, let's look at chlorine. Let's go ahead and we have chlorine and we're adding an electron to form the chloride ion, and it gives off 349 kilojoules of energy. Energy is given off. That means it's an exothermic reaction. And notice our electron affinity here is negative 349 kilojoules per mole. That negative sign just means that the energy was given off. So elements that have a negative electron affinity gain electrons easily to form those anions. There are some atoms that have no affinity for an additional electron whatsoever. The noble gases should be coming to mind. So something like helium, it already has a stable outer shell. It's completely filled S subshell. It really doesn't want any electron. So this reaction really doesn't happen. And so we just say that helium's electron affinity is 0. It really doesn't have any affinity for an electron at all. Well, our last and final property is called electronegativity. And electronegativity is the ability of an atom, when it's in a chemical bond, to attract electrons to itself. And so things that have high electronegativities are things that like to gain electrons, and things that have low electron affinities are things that like to lose electrons. And so in general, metals don't want their electrons. They would like to form cations, and so they have a low electronegativity. Where nonmetals, they want their electrons. They would like to gain more electrons to possibly achieve a stable octet and have a noble gas electron configuration. So nonmetals have higher electronegativities. So what I want you to do for tomorrow is I want you to go to this website, bookmark it. It's also put up on Moodle so that when class starts tomorrow, you have this website pulled up on your computer and we're ready to plot these trends. This website is going to give us values for our electronegativities, ionization energies, electron affinities, and radius. And you're going to be plotting what happens to electronegativity when you go across the periodic table or down the periodic table. And we're going to be doing that for all of these properties. So go ahead, look at this website, play around with it a little bit, and have it pulled up when class starts tomorrow so we can start our activity immediately and plot these trends. Have a good night.